First, let's start with why we need a system Verilog. So we will consider a design here. We have written some RTL code for this design, and we have developed some test bench for this RTL code for verifying our design. So we have already discussed in our Verilog sessions about how to write a test bench, not completely, but briefly we have discussed that how to write a test bench for a design which is written in RTL, and we have, I think we have developed a test bench for full adder in gate level modeling, and we have seen how this design is working for our given stimulus. So in the test bench, I think for our design we have two inputs, say a is equal a, b and carry in. For full adder in our design we have developed with our full adder with inputs a, b and c in. So in our test bench we have written we have driven the stimulus a is equal to 0, b is equal to 0 and c in is equal to 0, and we have written another case where a is equal to 1, b is equal to 0, c in is equal to 0 and a is equal to 1, b is equal to 1, c is equal to 1. So we have written this test bench, right? So and we have written this test bench, and we have driven the particular stimuli to our design, and we have captured the output, and we have analyzed that output. Since we have already know the functionality of this full adder functionality we already know, and then we already know what happens if we give a is equal to 0, b is equal to 0, c in is equal to 0, and we know what happens when we give this particular set of stimulus to our full adder like this. So we already know this, and we have, since we already know this, so the output which we got from our full adder by writing the test bench, we have analyzed it, and we have declared if we got right, if our output is correct, then we have concluded that our design is working perfectly. If we have not got that output, then we may conclude that our design is not working correctly. So as a verification engineer, when you are verifying the design, if the output is not according to the design specification, then you will inform the design team that the design is not working perfectly. So in Verilog also you can write this test bench and you can test the design. But when you are writing the test bench, you are in this scenario only, when you are writing this test bench, you are taking this scenario a is equal to 0, b is equal to 0, c in is equal to 0. So we have to drive three inputs with these many scenarios, like one, like one time this all should be 0, and another time we are making 1000, like there are multiple combinations involved here. Like if there are three inputs and three combinations like this, there will be multiple combinations, but we are only trying with the 1 2 3 4 combinations only in this TB. Are you getting right? Up to here, is it clear, right? Okay.
Yes, sir.
Yeah. So, so when writing in Verilog, we are considering only this four scenarios, but we are not considering the entire scenarios. Like there may be another cases also, like A may be equal to 0, B may be equal to 1, C may be equal to 0, but it may take a lot of coding. It will be easy only, but it will take lot of coding while writing or while testing these scenarios. So this is a small design with only three inputs, and let's consider another example of a RAM. So in this RAM we have a clock, we have data in, write enable signal, read enable signal, and what we have, data in, write enable, read enable, and a data out signal. Consider this as a 16 cross 8 RAM, means 16 locations. Each location is of 8-bit width. 16 locations, 8-bit. Each location is of 8-bit width. So 16 locations means 16 addresses we have. So for representing the 16 addresses, we need 2 power 4 is equal to 16. That means we need 4 bits. This we will discuss later, how to calculate these bits. So for 16 addresses, we need so there are totally 16 addresses. To represent the 16 addresses, we need 4 bits. So in this case, we have designed this RAM, and if we want to test this RAM, so there are total 16 locations in this RAM. Please listen this carefully. If you have any doubt, you can ask me. So in this RAM, we have 16 locations, and we have 1, 2, 3, 4 input signals. And let's say, and the data in width is 8-bit, and the data in width is 8-bit. So how many combinations are possible with this 8-bit data, 8 bits? So they are total
256.
2 power 8, yeah. 2 power 8 combinations are possible with this. So if you want to test this design, RAM design, you will start writing a test bench. You will start writing a test bench. You will first make this write enable signal is equal to 1, and you will give some data in this 256 in this 256 combinations. You will, at first instance, you will give some random first sequence, and if you want to read the data, you will make read enable is equal to 1. So this is what you will do, and the address is very important. So at some random address, so there are 16 addresses, right? So in any one of the address you will store, say suppose 2. So any random address you are going to store. So this is a particular set of sequence where you are storing data which is of 256 combinations. You are taking only one combination, and you are storing in a particular address where you have 16 combination of addresses, and in 256 combinations you are taking one data and you are storing in one address. So like this, you have total 256 combinations and you have total 16 locations. So there will be multiple combinations possible here. So writing the test bench for this many combinations is very complicated. So this is very complicated process, and you cannot test this 256 combinations in entire this 16 locations, and you cannot, it is not at all feasible. So this is where a concept called dollar random is used. So basically, by using this dollar random, uh, in Verilog we can generate random values. So instead of specifying values, hard coded values, we can use dollar random keyword and we can generate random values, and we can store them in different random locations. So we will use this dollar random keyword, we will generate random values, and we will store it in random addresses. So I'm talking still about Verilog only. So we will generate random values and we will store it in random addresses. So here, while verifying this RAM, we will individually test whether the data is storing in the correct, whether the data is storing in this location, whether there is any error while storing this data in this particular location or not. But this is also not possible if there are many locations, like say some 256 locations or so on. So for 16 locations we can do by using random. So this is where our Verilog test bench has got limitations, and we start using SV, system Verilog. So is this clear, right? Why we are shifting to system Verilog? Limitation of Verilog test bench, yeah. So why we are shifting to SV? So this is the reason. If there are many locations involved, then it is not feasible as to check individual location, and we cannot check whether the data is being stored in that location or not. So whether there is a bug in that location or some error in that location, it is not feasible. So in system Verilog, we will use random constrained verification. So by using this system Verilog concept, if we have a design, then by using randomly generated values, we are going to test our design. And by using and there is another concept called functional coverage. We are going to check whether all the possible scenarios, all the possible test cases, all the possible test cases are tested or not. So when we write and so this is basically a directed test case what we are writing in Verilog. So this is a directed test case. That means we are individually giving the hardcore values, but here in case of SV we are using random constraint verification. So here we will give random test cases, and we will leave it to the simulator to generate some random values and to store that random values in some random locations. And using the functional coverage, we will check whether we are testing all the possible scenarios or not, all the possible test cases are met or not. So by using this system Verilog, we are going to check the design completely. Like we are going to the simulator. So after the coding, after completing the coding part, by using the functional coverage, we will check whether our design can able to perform for all the random stimuli or not. So this is the use case of system Verilog. So by using the system Verilog, we can check our design completely. We can cover all the possible test cases by using our system Verilog. So is this clear for everyone? Is there any doubt in here? Yeah. So this is why we are shifted to system Verilog for verification instead of Verilog. We can also verify our design using the Verilog, but why we are shifting to Verilog is this reason. So this is the introduction to system Verilog. So I don't want to waste more time discussing about why we want system Verilog and stuff. If you have any doubt why we want system Verilog more, then you can ask me. So from tomorrow we will start directly with system Verilog data types, constructs, and we will see one by one how to verify the design like that. So this is a basic introduction to usage of and need of system Verilog.